Welcome to 51st lecture of this open course on diffusion in multi-component solids. In the last class, we have seen how the diffusion structures develop in a multiphase diffusion couple and how we can use them to get some information about phase diagrams. Now, this class I would like to explain how we can analyze the diffusion profiles developed in a multiphase diffusion couple. So, let us consider one concentration profile in a multiphase diffusion couple. Let us say this is C A minus, this is C A plus, and this side is alpha, this side is beta, and there is an interface at xi which is, let us assume, a planar interface. So, there will be a discontinuity in the profile at xi. So, the profile would look something like this. So, this is C A alpha, this is C A beta. Now, we can use the same principles to analyze this as we used for the single phase diffusion couples, as long as we assume molar volume to be constant. So, for constant molar volume, we know for finding the metanoplane, which is the first task in the analysis of diffusion profiles, we can use the formula integral minus infinity to plus infinity x minus x naught dCA equal to 0. Now, to understand this, let us split this integral at different places. So, let us label these points A, let us say this is the position of metanoplane x naught, this is A, B, let us call this C, D, E, F, G, H and I. So, let us split the integral at two positions at the discontinuity in the concentration profiles at the interface. So, we can write this to be minus integral minus infinity to C x minus x naught dCA plus integral C to E x minus x naught dCA plus integral E to C at x naught, that is the position G, x minus x naught dCA plus integral G to plus infinity x minus x naught dCA. So, if you look at these integrals, the first integral minus infinity to C, this area A, B, D, C, A, and the sign would be x minus x naught is negative and dCA is negative because CA is decreasing. So, there would be a positive sign. The integral from C to E would be again this area C, D, F, E. There will be a positive sign, and integral E to C at x naught is this small area E, F, G with a positive sign. Then the integral G to plus infinity would be this area GIHG, and there will be a negative sign because now x minus x naught is positive, but dCA is still negative, should be equal to 0. So, this basically tells me that this total area, let us call this P, should be equal to this area Q on the other side of the metanoplane. So, a similar procedure can be applied for finding the metanoplane. The same equation can be used for finding fluxes as we used for single phase diffusion couples, that is J tilde at any position x should be equal to 1 over 2 t integral minus infinity to c at x minus x naught dc. So, if we consider again a concentration profile in a multi-phase couple, let us say Cm, and let us say this is the metanoplane position here. This is the interface position xi. If you want to find out the flux at a point, there is a discontinuity here. Let us label these points A, B, C, D, E, F, G, H, I, G. So, if you want to find out the interdiffusion flux at point E, that is on the alpha side of the interface, we know it will be basically 1 over 2 t times this area A, B, C, D, E. So, J tilde at E would be 1 over 2 t times area A, B, C, D, E, A, and component is moving from left to right here. So, the diffusion flux will be positive, which is also clear from the signs here. X minus x naught is negative and dC is negative. So, the flux would be positive. After the discontinuity, that is on the beta side of the interface, what would be the interdiffusion flux? Now, it would be J tilde at F. So, it will add another area here EDGF, and so the J tilde at F would be 1 over 2 t area A, B, C, D, G, F, E, A, and again it will be a positive value. Now, and the diffusion flux will keep increasing until the metanoplane position, similar to in the single phase couple. After the metano position, the sign of x minus x naught changes, and so the contribution of the further areas will be negative, and hence the flux will start decreasing. There will be a maximum at the metanoplane. So, if you draw the diffusion flux profiles, this is xi, this is x naught. You know the diffusion flux is positive, it increases, and suddenly there is a jump at the discontinuity, that is at the interface, and then it increases again until the metanoplane. At the metanoplane it reaches maximum and then start decreasing. So, similar to the concentration profile, there is also a discontinuity in the flux profile. So, at the discontinuity we can say this is the flux of component A on the alpha side of the interface, and this is the flux of component A on the beta side of the interface. If we look into the diffusion structure, there will be a planar interface between alpha and beta, and A is moving from left to right. There will be some flux coming in to the interface, which is J A alpha, exactly at the interface position. And there will be some flux leaving the interface into beta, this we call as J A beta. So, this is how the flux profile. So, this is how the flux profile would look like in a multiphase diffusion couple. We can similarly draw various types of flux profiles, which I will give you in the exercises. Now, the question is, how do we use this data? Once we evaluate the diffusion flux profile, how we can make use of it? Obviously, with the multiphase diffusion couple, using the same approach as for single phase couples, we can also determine the interdiffusion coefficients. So, for binary, single couple would be okay for determining interdiffusion coefficients at different compositions. For ternary, we will need two couples with intersecting diffusion paths and so on. However, the error would be more because we are assuming constant molar volume. But in multiphase couple, by its nature, there are two different phases at least present, and the two phases would tend to have different molar volumes, and hence the error involved because of assumption of constant molar volume would be more. However, by knowing the fluxes and compositions at the interfaces, we can get a quantitative estimate of the velocity of the interface, which is important for getting the idea about the growth rate of a phase. Let us see how we can go about it. So, let us first try to see how we can get the velocity of interface. Again, I am showing a concentration profile in a multiphase couple. Xi is the position of interface, x naught is the metanoplane. On the left side I have alpha phase, right side I have beta phase. So, obviously, as the diffusion progresses, one phase has to grow at the expense of the other, and hence the interface has to travel. So, it is important to know at what rate this interface is travelling, because that way we would need that way we can estimate the growth rate of a particular phase. So, let us say this interface at xi at time t is moving with a velocity v I. So, v I is nothing but dx by dt for xi. So, if I assume, if I consider a very small element of width dx around the interface, suppose this small volume, and since I am considering a unit cross sectional area, volume of this element is dx. Suppose the interface is moving so that the beta grows at the expense of alpha in time, a small interval of time delta t. Suppose the beta is growing at the expense of alpha, and in small interval of time delta t, the small volume dx is converted from beta into from alpha into beta. So, initially the small element had the concentration C A alpha, and it has changed in small interval of time delta t to C A beta. And if J A alpha is the interdiffusion flux of A at the interface on alpha side, and J A beta is the interdiffusion flux of A at the interface on beta side, then we can write, since we are considering unit cross section, the mass balance as the final concentration Ca beta minus initial concentration Ca alpha of the element times the volume of the element, which is dx, is equal to the difference in the fluxes Ja tilde alpha, this should be tilde because I am considering interdiffusion flux, Ja tilde beta minus Ja tilde alpha times the unit cross section 1 times the time interval delta t. So, this tells me as delta t tends to 0, dx by dt, which is nothing but Vi, should be equal to Ja tilde beta minus Ja tilde alpha divided by Ca beta minus Ca alpha. This equation can also be obtained by simply considering the frame of reference which is fixed to this interface. Since the frame of reference is fixed to this interface, the flux in that frame of reference, let us call it Ja phi, should be equal to the interdiffusion flux J tilde A, if I consider in the alpha phase, J tilde A alpha minus Ca alpha times the interface velocity. This we can also consider in the beta phase, and so we can also write Ja tilde beta minus Ca beta times Vi. And so, the formula for Vi can be obtained as Vi is equal to Ja tilde beta minus Ja tilde alpha divided by Ca beta minus Ca alpha. And this is very important because this way we can, use for analyzing the growth rates. So, for example, consider the growth of a precipitate beta in the matrix alpha. So, this is beta and the matrix is alpha. Obviously, the precipitation is occurring because the matrix is supersaturated with the solute. Let us call the solute is I, and hence the solute has to be transported from matrix to the interface. So, there will be a negative concentration gradient with respect to this interface here, and the concentration in the matrix in the precipitate will be of course higher. So, let us say the concentration gradient here is something like this. Now, as the beta grows, this interface is moving into the matrix, that, and similarly the other interface is moving towards left, and that is how the beta precipitate would grow. So, to evaluate this growth rate, it is important to understand the velocity of this interface, and the velocity of this interface can be obtained by the formula that we derived. Vi is equal to Ji tilde in alpha, Ji tilde in beta minus Ji tilde in alpha divided by Ci in beta minus Ci in alpha. Most of the time the precipitates are line compounds, which means there is no concentration gradient in the within the precipitate, and hence we can assume safely that Ji beta tilde to be 0, close to 0, and so we can write Vi, if we use Fick's law, minus d alpha times dou Ci by dou x in alpha. So, this would be d tilde alpha, that is the interdiffusion coefficient in alpha, times dCi by dx in alpha at the interface divided by Ci beta minus Ci alpha. So, let us consider for example, two different cases that will help us to understand how different concentration profiles are developed depending upon different transformations. So, if I consider precipitation of, let us say, carbide in austenite, it will be a similar case like this, because carbide concentration is higher. So, the precipitate concentration Ci beta, let us say carbide is beta, austenite is alpha. So, the precipitate concentration Ci beta would be greater than the matrix concentration Ci alpha. Since the carbide has to grow, this interface has to move from left to right, that is from the precipitate side into the matrix, which means Vi has to be positive. Since Ci beta, that is carbide concentration, is higher than the matrix concentration, that means the gradient in alpha has to be positive also, and so this kind of gradient will be set up. Physically also it is understood, because for the carbide precipitate to grow, the carbon has to be transported from matrix towards the precipitate, and hence the carbon concentration gradient here with respect to this interface should be positive. What happens if ferrite is growing in austenite? Ferrite is alpha, austenite is denoted as gamma. So, in this case now ferrite has of course lower concentration of carbon than gamma and austenite. That means, and Vi, the interface velocity here would be given by Vi is equal to d tilde gamma dCi by dx in gamma divided by Ci alpha minus Ci gamma. Now, ferrite concentration, carbon concentration in ferrite is typically very small, and so it can be taken as constant. So, still the similar formula can be applied. Now, in this case, for the growth of ferrite, again the interface velocity has to be, for the growth of ferrite again the interface velocity has to be from left to right, that is positive, but Ci alpha here is less than Ci gamma, and so this term is negative, and that is why the gradient has to be negative. That means, in gamma the gradient will be developed something like this. Negative gradient, which is also understood again physically, because ferrite has much lower carbon concentration than austenite, and hence when the ferrite is growing in austenite, the excess carbon has to be rejected into the matrix, and therefore the negative gradient will be developed with respect to this interface here. So, this is how we can use the multiphase diffusion analysis in actually determining the phase growth rates. Simple interdiffusion flux and concentration analysis help us to get to the interface velocity, which in turn helps us to understand the growth rates, and that is why studying multiphase diffusion is important. We will stop here today. Thank you.